Hello everyone. So today we're going to study what I find is one of the most interesting op amps, and well, this one it's called a summing op amp. We'll see why it's called a summing op amp, but I think you can take a gander at it, and it looks something like this. And well, first things first, one thing is I want to be a bit less reliant on drawing cells, okay, for these op amp circuits, because it's just to emphasize the fact that it's not really necessary that the voltages that we're talking about, the supply voltages, they don't necessarily need to come from cells, okay. So long as it comes from somewhere and we know what the voltage is, that's all that we need, okay. And especially when we do those problems which have multiple op amps, will be in a later video hopefully. Um, those those you know those voltages would actually, the voltage for one op amp would usually come from another one, okay. So that's why it's really not necessary for you to like have a cell here, okay. So long as you know what the voltage is, um, it's all fine and well. All right, so it doesn't matter if it's all right, so that's enough for that. So this op amp basically, you have these potentials, okay, voltages. Then you cross these resistances, and you have this single path to your um, inverting input. You also have the feedback resistance, and your non-inverting input is connected to the ground, your virtual ground. All right, so um, all right, we see the structure now. Why is it called a summing op amp? Again, what's going to be the formula? Well, let's find that out, right? So, first things first. Let's try to find um, some some voltages here. So this one, this whole node, right? This whole node is, oops, this whole node is the ground, right? So this our non-inverting input, okay, that's V2, is going to be 0 volts, right? And so if that is 0 volts, since this is an ideal op amp, we're assuming it is so. Our um, why is the pen so rough? Okay, our non-inverting input, this also has to be 0 volts. Okay, so V1, um, yeah, this is equal to 0 volts. This is, yeah, okay. So that's done, and we also know, just like we have been doing until now, the currents at the inputs, they are zero. So this current, let's see, this current right here is going to be zero. Okay, all right. With that done, now for the moment, I'll just say that the currents here, let's pick a suitable color. Okay, I'll just say for now that the currents here, okay, like this one through R1, it's I1. This one is I2. Okay, this one is I3. Okay, let's just keep it at that for now. We'll expand that later. And okay, so this is V naught, right? This is V naught. Okay. Let's see. Yeah. So we have pretty much set up everything that we need for KCL, okay, or nodal analysis. We see that, okay, so here you have a current, okay. Here you have a current. If you consider this node, okay, if you do nodal analysis with this node, we see that the current entering, okay, these three, the sum of these three, and yeah, by the way, I'll talk about that a bit later too, but it's not necessary you have three of these. We'll see that a bit later. But again, I'm just saying, okay, not necessary that there's three. There could be five, seven, as many as you want, or even two. And we'll see something a bit more interesting if you have it as one. Okay. So, anyways, that's for later. One of these. Okay, so what do we see? So the current entering, the sum of these three currents, okay, is going to be equal to the current exiting. This one is zero, doesn't matter, and this one is the current exiting. So let's set up our KCL equation. We have the current entering, which is the sum of these three. So I1 plus I2 plus I3. Okay, this is gonna be equal to the current exiting, right? Which is our voltage difference divided by the resistance. So voltage difference here is 0 minus V naught, right? The current is flowing here, okay, in this direction, divided by the feedback resistance. Okay, so 0 minus V naught divided by the feedback resistance. Zero doesn't matter, and you basically have negative V naught here. So if I cancel this out, you basically have negative V naught here. And if I multiply both sides by negative of the feedback resistance, I'll do this in a different color. If I multiply both sides by negative R sub F, what I get is the output voltage is actually equal to the negative of the feedback resistance times I1 plus I2 plus I3. All right. So actually, this is actually one form of writing it, and personally, I like this one a lot. Maybe the most, to be honest, from the forms that this can be written in, particularly because it really showcases why this is called showcases pretty simply why this is called a summing op amp. Okay, you take the currents, you take you could say your supply or input. I'll not say input currents, but anyways, you take your currents. Okay, actually, basically, it is the current that's flowing here. Okay, the total current here is going to be same as these. But anyways, you take the all the currents in the branches that are entering, and you add them. Okay, you sum them. Okay, so this is where the name comes from. You sum them. Okay, you add them, and then you just multiply that by the negative of the feedback resistance. Okay, the negative of the feedback resistance, and you get your output voltage. Okay, this is one form of writing it, but as we've seen, usually it's where we write these in terms of the supply voltage, right? And these are the supply voltages. Okay, these ones right here. So let's try to write this actually in terms of the supply voltages. If we were to try to do that, just suppose, say, if we just talk about I1. Okay, this is going to be equal to the potential difference divided by the resistance, right? The voltage, or PD. Okay, so it's V1 minus, see here, this whole node, as we have said, the voltage, the potential is 0 here. So V1 minus 0 divided by R1. Okay, so the 0 doesn't matter, so this is going to be V1 by R1, and the rest is pretty much the same to V. I2 is V2 by R2, I3 is V3 by R3. Let's substitute all that. What we get at the end is our V naught is gonna be equal to the negative of the feedback resistance multiplied by V1 by R1. Okay, that's I1, right? V2 by R2, V2 by R2 plus V3 by R3. All right. This is how the final result is usually written in books. Now, and the way it's said is that the summing op amp takes your supply voltages. Okay, takes their weighted sum. Okay, you could call this a weighted sum, weighted on the basis of the resistances, okay, to which the potentials are connected. So it takes the weighted sum of the supply voltages, and then it just multiplies that with your feedback resistance, the negative of that, actually the negative of that. All right, so this is basically the formula of the summing op amp. In general, as I said, you don't. It's not necessary that you have two of these branches right here. Suppose you have n of them. Okay, if you have n of them, in general, we could just say, why am I switching to red again? That's an overuse of red. Okay, if in general, we have n branches, we could just easily say that your output voltage is gonna be the negative, negative feedback resistance, and the sum, okay, multiplied by the sum of your input sorry, the supply voltages divided by the corresponding resistances. Okay, the sum up to your n branches. All right. Yeah, so this is how you could generally write it. Don't exactly need the n, the sum, the sigma makes it pretty clear. anyways, so that's the formula. But what I wanna actually talk about now, it's not necessary to know per se, but I think many of you are noticing this, and it's good that you are. It's actually, one thing is, see, look at this formula right here. Isn't it pretty similar to something that we did before? Uh, the inverting op amp per se. Okay, it's pretty similar, right? The formula here you have negative, the feedback resistance, and if you just rearrange this, this would be basically negative feedback resistance multiplied by V1 divided by supply voltage. You basically have one of them. That's why. Um, it is Vs, but let's just write that as V1, right? Uh, just make it a bit similar to that. So um, here your supply voltage V1 or Vs, whatever you want to call it, divided by R1. This is this is actually these two actually look pretty similar, right? Where did that go? These two look pretty similar. Just if in this formula you didn't have the other terms, you didn't have the excess terms, okay, this would be your only supply voltage, right? It is a supply voltage just like that one. Like let's see, this inverting op amp, I already said that it doesn't necessarily have to be a cell, okay? So it is really the same. It is really the same as what we have here, okay? Just you have a summing op amp, it would basically become an inverting op amp if you only have one branch, right? If you only have one branch, the circuit would obviously become exactly the same if you just eliminate the other branch. You have a voltage here connected to some resistance, and then the rest. So um, another way, so what I said right now, so the summing op amp is if you just remove the other branches, just have one branch, it basically becomes an inverting op amp, or how it's usually said. Okay, I find it more neat is that the summing op amp is just a variation of the inverting op amp. Okay, summing op amp, it's a variation. Okay, a variation of the inverting op amp. Okay, variation. Okay, or just a modified version of inverting op amp. All right, so the only thing is that it takes more supply voltages or inputs, okay, compared to the inverting and inverting op amp. But really that's about it. And there, I might be blabbering unnecessarily, but there are really a couple of ways you can look at it. One way to think about this is, okay, so you have the summing op amp. Try to solve this problem instead of how I did this. I really encourage you to do so. Try to solve this using superposition. Okay, you can think of these like you can just think of this circuit. Suppose, say, if you had, whoops, this you could just very easily replace this with some cell. Okay, if I want to think about it like that, okay, which has a voltage of V1. Okay, and well, this has to be connected to the ground. I could connect it here, but I know that the diagram is gonna become super messy, so I'm not gonna do that. So could say this is V2. Yeah, these are connected to the ground. So I really encourage you to, it's really the same circuit here. It's really the same circuit here. And I encourage you to solve this problem not the way I did, but using superposition instead. Okay. And what you see is when you just take one of these cells, when you consider one of them and turn the other ones off, which you need to do for superposition, you see that the other resistances, they won't have any current across them. Zero volts here, 0 volts here, no potential difference. They don't matter. You can just eliminate them. Basically becomes an inverting op amp. Okay, for the each case for the superposition you consider. Okay, and you're basically then just adding up those voltages that you get, right? Basically then add up all the individual voltages, output voltages that you get. So summing op amp, it's basically a superposition of inverting op amps. Okay, that's I think the best way to put it. Or if you even want to think about it another way, this is, again, if some of you are familiar with this, if you have studied a lot about batteries in parallel and stuff, if you think about each of these as a battery with an EMF and an internal resistance. This is actually just a set of batteries in parallel, and if you remember the formula for the EMF of batteries in parallel, this is basically the EMF divided by the internal resistance. The equivalent of the equivalent battery. Anyways, that's enough discussing of that. Okay. Um, Mainly what I want to say is how the summing op amp is related to the inverting op amp. Let's actually try one problem. All right. So the problem we have is this one. No, before that, I just forgot to mention this, but because as we said that summing op amp is basically just a modified version of the inverting op amp. One of the most important things is that it does, in fact, like the inverting op amp, it inverts the polarity of the supply. Okay, the output has the reverse polarity compared to the supply. All right. So, with that said, let's try out this problem. And well, it's just drawn a bit differently. As you can see, you have three pairs of cell connected to resistors. Okay, um, this is just drawn a bit differently than what we had here. Okay, but it's really just the same thing, right? It's really just we just rotate this by 90 degrees. You just get this. So yeah, basically what really matters is these three branches are yeah, these are connected to our non-inverting. Okay, yeah, I forgot to label that. So this is not non-inverting, this is the inverting input, this is the non-inverting input. So what's important is these three are connected to our inverting input, and yes, we have the feedback. So basically everything is saying is that this is, in fact, if you wait, let me just scroll up a bit. Okay, so this part right here, excluding that 4 ohm resistor that we have right there, um, this part is basically a summing op amp. Okay, this part is a summing op amp, and so if it is, we can, well, the question is that we need to find the output voltage. Okay, that should be easy, just apply the formula, and then we need to find the output current. Okay, um, we'll see that in a bit. First, let's try to find the output voltage and then see what we can do about the other one. So the output voltage it's basically going to be, let's try to find that. Okay, so let's see. We have the output voltage is going to be equal to, first thing first, it's gonna be our you know our feedback resistance. Actually, I'm gonna leave the kilos as it is. I think you can see that those are gonna cancel out anyways. So I won't expand that. So negative 8 kilo ohms, right? Negative 8 kilo ohms. This is our feedback resistance. Out somewhere. Okay. So negative 8 kilo ohms multiplied by um, the weighted sum of these voltages, right? Which are here provided by cells. But again, I'd like to emphasize that it doesn't need to be provided by cells. And I uh, another thing which I haven't said explicitly, they don't even need to be constant. Okay, it could be some AC signal, it could be anything. It doesn't really have to be constant. It could change. All that matters is that we have an expression for this, for these supply voltages. Okay, and well, here it's pretty simple. All of these are coming from cells, they're constant, and yeah, so the weighted sum of these compared, based on the resistances. So we have 1.5, and the resistance associated with that is 20k. 20k. Let's see. Plus 2 volts. Okay, 2 volts divided by 10k. Okay, 10k plus 1.2 divided by 6. Oops. 1.2 divided by 6. uh okay, 6 kilo ohms, actually 6k. All right, so let's move on. Well, as you can see the kilos actually cancel out. I'll change color. So the kilos actually cancel out here. The calculation here is, we I press this in the calculator. It's equals, and what I get is negative 3.8. Negative 3.8 volts. So write that down. So the output voltage, that's one of the things that we need to answer, is negative 3.8 volts. fascinating. We got that pretty easily. With that done, let's try to find the output current. Okay, this one. And to do that, um, I think the best, there are, three wires, okay, connected to this node. Okay, one of them is, the current, it carries that current that we need. KCL would probably be best, but first we need to figure out some things, how to find these currents. So one thing is this, this is just the same node, right? This is just the same, this is the same node. So obviously the, voltage here is V output. So first thing is, this current right here, we can easily find that this is the ground, the voltage difference, V naught by the, divided by, sorry, minus 0 divided by 4K. That should be easy. This one too, as I said, since this is 0, this is 0, this is 0, the inverting input also. So this is V naught minus 0 divided by 8. That should be this current. Okay. So these two are the currents that are exiting. Okay, you could say that node. These two are the currents that are exiting that node, and they have to be equal to this current that's entering this node, right? So let's actually write that down. Our output current is equal to, it's the current entering is going to be equal to the two currents that are exiting. This one is what? V naught minus 0. So we have the ground divided by 4000. Okay, 4000 4k ohms. So and we know V naught, this is negative 3.8, divided by 4000. The 0 just disappears. Also, this is added with this current right here, which is, let's see, V naught again minus 0. This is 0 volts. Oops, that was pretty light. This is 0 volts. Okay, so V naught minus 0, V naught minus 0, divided by 8 kilo ohms. So 8000. All right. So let's see. V naught, which is negative 3.8 again, divided by 8000. All right. So this should give me my answer. Let's actually find that. So what we have here is, I'll factor out the V naught, uh, negative 3.8. Oops, no, 3.8. Okay. We have 4000 inverse plus 8000 inverse. So this should give me my answer. It is, okay. So negative 1.425 times 10 to the minus 3 amps, or 10 to the minus 3. I think most of us should get this tendency if we are not too strict about. Well, it is an SI unit, just has a prefix. This is more convenient to write in milliamps. So this is negative 1.425 milliamps. All right. So that's done. That is basically our output current. Okay. It took some logic, and especially there's really for these op amps, they could be used in very different situations. Okay, so there's never really a constant formula for the output current. Okay, I just need to find that manually. So we were still pretty easily be able to solve this problem, which I know, if after if we just learned about ideal op amps, without touching these particular modules, this might have seemed like a very difficult problem. Nevertheless, this is solved. So I think that should be all for summing op amps. We should be doing, I think it's the the difference of op amp, or yeah, yeah, that's gonna be next. So see you in the next video. If you appreciated this video, if you found it helpful, please leave a like, please subscribe. Also, if you have any suggestions, or if you found any issues in the video, please do leave that in the comments. So goodbye and study